Okay, so in the previous class we were discussing about shell scripting. I did share some notes. I'm not sure if you have practiced it, uh, but these are some advanced stuff. Okay, up till here I had discussed, I think, string variables comparison, but after that it's little advanced. So I was thinking if you guys first complete it till here, because I'm sure many of you haven't even tried it. Okay, but it is a little important to understand these basics before moving on to the more advanced scripting stuff. So I'll give you some more time. Practice it whenever you get time. Practice at least the basics scripting things, and when you're comfortable, I can discuss these advanced also in any of the coming class. So it depends upon how much confident everyone in this class is about the basic basics of the scripting part. So I will not continue from here, but yes, these are still available in the notes. People who have already done it, you can refer these notes and practice out for yourself. But we will continue with our Hadoop uh, services for now. Probably when we are done with it at the end of this course, if you are comfortable with the basics, I will take you to the more advanced scripting topics. Okay, so let's come back to Hadoop. So in Hadoop, we have completed the HDFS service, and that was basically the distributed storage layer. Today we will start with the computational layer of Hadoop. Okay, can anybody explain me what exactly is yarn? If you have already studied about it, this looks fine. Okay, yarn. So yarn stands for yet another resource negotiator. Okay, so far we discussed about the storage of big data. You know how we stored our big data in distributed yet resilient in terms of high availability environments, and that was basically used on commodity hardware. But now comes the actual part that deals with businesses. That's about bringing out insights out of this data. Okay, then it's about bringing insights useful for the business, we need a computational layer over HDFS for the data, right? That is basically your yarn. It sits above HDFS layer. Okay, so it sits above HDFS. It extracts the data from HDFS. Well, I cannot say it extracts it. Basically, we run computationals over the HDFS at the same place where the data is present. And once we have done our computational, we have got the insights. The results are again stored back in the HDFS layer. Okay, so there is one more concept called as data locality here, which means code is shifted, or code is, we can say, exported to the place where data sits instead of the other way around. Okay, so this is the core essence of yarn. Now, what the traditional computational such systems such as RDBMS, or if some of you are familiar with SQL languages, if you have heard about something called as relational database system, I've discussed about this when we were starting with HDFS also, and with the Hadoop also, and I told you how these kind of system, we also call them as SQL systems, how they are not compatible enough for handling big datas, and this is like another shortcoming of relational databases. So we have already discussed about how they are not suitable to handle large data sets or large data or something, because they are actually not architectured for large data, and wherein we need more storage and more RAM to process out of it, and how they were not suitable enough to be converted into distributed environment. Similarly, when it comes to computation, similarly, these systems are not architectured to run efficient computation over large data sets. And how? So one of the primary reasons of its failure, one of the primary reasons why RDBMS failed to run efficient computation over the data which was stored, somehow let's say that it managed to store the large data, but when it comes to running computation, it failed. The reason being, it runs behind the core concept of it expects the data to be transported to the place where computation runs. To make you more understand about this, let's discuss our own architecture itself. Okay, so we have three servers. We have a server 1, we have a server 2, and we have server 3, and all of them we have data nodes, right? So we have data sitting over it. Let's say replace, instead of data nodes, we have this RDBMS system over the three of them. Okay, so let's say I would have an RDBMS system over these three of them, and they are all storing data. Okay, for the sake of this example, let me also consider that I have another system S4, another server S4, which is just a client. Okay, so it's just a client which will connect to these RDBMS systems, and over this client is basically I'm going to run a code. Okay, so let's say in RDBMS system, the data which I have already stored is the employee information. Employee data is being stored in all of them. Okay, and this data is pretty large. Let's say it's in terabytes, or I can say my customer data, employee data would be not be that much of large. So my customer data, which is in terabytes, let's say 5 terabytes. Okay. Now when it comes to RDBMS, whenever I would run a code, so let's say I want to understand how many of the customers, so what was the spending average spend done by each customer. So I wrote some logic, some code to get this information, to analyze this data and get the information out of it. Now when it comes to RDBMS, when I run this code, the RDBMS system expects this data to be transported every time to the client. So every time this code is run, this data would need to be transported to the client. Client will do its processing, then client processes the data, and once the processing is done, the results are again transmitted back to the system. So these results are again expected to be transmitted back to the system. Now this was working fine. Such an architecture which expects the data to be transmitted over the network every time, over the network to the place where analysis is to be done, was fine enough when the data was small in quantity. But as the amount of data starts to grow, it can be disastrous to transmit data every time. Okay, so for small data, this was easy. Let's say if data was in megabytes or even in gigabytes, to transmit it over the network to the place where code needs to run, and then after that getting the results. This was fine for smaller data sets, but for something which is as big as in terabytes, this is definitely not a viable option, because it might take days, or even it might take even a month to, let's say, even transmit this data. So what the architecture of Hadoop thought of, that instead of transmitting this data, because let's say if I write a code, okay, if I write a logic into a file, that's not gonna take more than let's say 1 GB would be very large file, I would say, when it comes to writing some code. It could be in megabytes, and that also very few megabytes. Okay, so the architecture of the Hadoop thought that instead of transmitting this data, why not transmit this code to the place where this large data sits? That seems more logical, right? So instead of moving this big data, we should move the smaller file which contains the logic to the place where the data sits. Then over that smaller file would be run over the data sets, and the results would be again combined together to come out of a final result. So this concept of moving the code to the place where data sits is called as data locality. That means the data will remain local, but the code will be foreign, and ultimately the results are stored out of it. So this is the first concept when it comes to learning about Hadoop, and learning about Yarn, especially the computational power of the distributed environment. Okay, so this was about how Hadoop functions in terms of computation. Now let's talk more about within Hadoop how it evolved. Okay, so before having this yarn, so yarn is basically, you can also call it as a MapReduce 2, or we can say version 2. But before this, the first architecture was basically only of MapReduce. So this was in Hadoop 2, Hadoop version 2, that we have yarn. But this was in Hadoop version 1. That's pretty old version, initially which came up, and in that version we have only had MapReduce, which was also called MR1 or MapReduce 1. So there are some even better approaches which Yarn has over MapReduce version 1, but we need to understand what exactly those are. Okay, so we will talk about MapReduce version 1 first and its architecture. Uh, yes. So again, similar to how we discussed the architecture of HDFS, right? We had a name node which was the master. Then we have data nodes, which were our slaves. Similar to that, Yeah. Okay. So similar to that architecture, we had this architecture on the computational end also, and the two major, similar to the name node, which was acting as a master. In here, the master was called as a job tracker, and it had multiple slaves, which were called as the task trackers. Similar to how in storage end we have data nodes. Okay. So most of the time, these task tracker are actually sitting on the same server, which had the distributed data node component of HDFS, to deal with, to be compliant with the concept of data locality. Okay. Okay. So this was the our master, only master that we had, called the job tracker, and these were all are my slaves in Hadoop version 1, called the task tracker. As the name suggests, task tracker will run smaller chunks of tasks, and the job tracker is only going to manage the jobs. It's not going to run any task, similar to how the name node only keeps the track of each data node as well as what data is stored in the cluster instead of actually running or storing some data. Similarly, what it happens in here also. Now you can see each task tracker is running on the same server which had data node. This because we have to be compliant with the concept of data locality. Now let's say I have a client, similar to how we discussed in RDBMS environment. So if this is my client and it wants to run some logic, okay, on the Hadoop side. So this client will pass on that logic, or let's say there's I want to run a Python script which has logic to calculate the average customer spend. Okay, so this is my code which I want to run. So my client will submit this code or pass this code to the job tracker. Now it is job tracker responsibility to distribute it to each of its task tracker. Okay, this phase of transferring the code to each task tracker and then mapping it to the corresponding data stored on the data node. Okay, so let's say that 5 terabytes of data that was basically distributed among these 3 data nodes. We all know that in Hadoop, in HDFS, we are actually storing data in a distributed fashion, right? So we have to, when we want to run something like this over the complete data sets, although it's present in distributed, but we'll have to run it in, we'll have to get the complete or a single output file out of it, right? So first of all, I will distribute it to each of these task tracker. They will map it to the corresponding data over which I want to run this analysis. This phase is called as the mapping phase or called as a mapper. Maps the code segment to the data stored on each data node and runs the analysis over that data set Okay, so this task tracker will run this analysis only over the data which is present on this data node. Similarly, the second task tracker will run only the analysis only over the data segment which is present on this data node, and similarly for all the other data nodes that you have in the cluster. Okay, so this is actually called as a mapper task or a mapper simply. Okay, so this task tracker is running a mapper. Similarly, this task tracker is also running a task called mapper, and similarly all the other task trackers. And what exactly is this mapper doing? It is just running this logic over the smaller or the part of the data which is only stored on that particular data node only. Okay. Now this mapper is going to store some of its files. So whatever output of the analysis is generated out of the data segment present on this data node, it is going to store on itself. Similarly, all the other data nodes, whatever analysis is done and the results are taken out, will be stored individually by them. Now then, since I want a single output, you know, so let's say if I have n number of data nodes, n number of data nodes are actually storing the analysis output of each data segment over which the mapper ran. So I would actually have n analysis outputs, right? But I want to generate a single output out of these n number of segmented outputs. So to generate a single combined analysis output of the code segment of the code or logic that we ran over the distributed data, we have this task called, we have the task in MapReduce called reducer. Okay, what this reducer will do, it will combine the outputs from n data nodes to generate a single output that can be read by a client, by the client. Okay, so finally, my client expects only a single file of analysis, right? It doesn't want distributed analysis done over smaller segments of a larger data file. But so to deliver such a single file, we have to have some task that will combine the outputs of each analysis done on each of these nodes and return that single analysis file, right? That is basically done by the task called reducer. Now this reducer will also run on any of these task types. Okay, so for our scenario, let's say this task tracker was running a mapper. This was running a mapper task. This was also running a mapper task. I'm putting it in bracket so that you don't get confused with the roles. It's not a role, it's a temporary task which is running over the task tracker. And for the third task tracker that I have, this is basically running two tasks. One is a mapper, other is a reducer. Okay, and the results, the final results of analysis are again stored back to HDFS, from where the client can read the output. Okay, so how is it beneficial? Let's, in terms of the RDBMS that we were discussing. So now we have included the concept of data locality, where we are transmitting this smaller file, which is in, let's say, in kilobytes or megabytes, over the place where we have data. So we are not jamming our network. And finally, we are using the concepts of distributed computing. So, instead of running this logic over the complete file, we are actually distributing it into multiple smaller files, which was basically handled by the HDFS layer. And then we are running this segment parallelly over multiple task trackers, and we are parallelly running, so that we are also reducing the time of our execution, as well as we are optimizing the process run. So that's how the Hadoop is beneficial also when it comes to run a distributed computing or distributed analysis of the data. Now, Yarn, when it comes to Yarn, it's basically Hadoop 2. It's a better version of the MapReduce. So this kind of an architecture, which is actually running a mapper and a reducer, is called a MapReduce architecture. But this also had some, disadvantages, some shortcomings, which were handled in the Hadoop version 2, or something called as a Yarn. Now, what are the shortcomings which were handled? Okay. So shortcomings of MapReduce 1. Number 1 was it had a single master, which is called as a job tracker. Okay, the single master or the job tracker. So it's actually acting as a single point of failure. If this job tracker is down, everything is stopped. My client will only contact job tracker, but if it's down, I cannot run anything over the cluster. So it's acting as a single point of failure for me, which is not acceptable. I must have something like a master slave architecture over this layer also. Okay, this is number 1. Number 2 is too much responsibilities to the job tracker. Okay, so this job tracker is not only managing, so this was only one job, let's say. This was only one logic. I could have hundreds of clients, hundreds of clients who are giving their own logic, which we have to run over the data sets and give them the results back. So there can be hundred of tasks running, hundred of such MapReduce jobs, running within the cluster. Now this job tracker is overburdened by many responsibilities, which include to track each job, each job which is running in the cluster, to manage the resource requirement of each job, to reinitiate the failed tasks which can be either MapReduce, Mapper, or Reducer related to each job. All such things are being handled by the job tracker, which is very tiresome for it. It can be a scenario where it fails because of such, overburdening of its resources. While when it comes to task tracker, it is just tracking the single mapper task or reducer task, or let's say if there is a mapper and reducer task associated with that particular job. Only its responsibility is to run that task and nothing else, while job tracker is doing a lot of stuff. So this is also a shortcoming of the MapReduce version 1. And the final shortcoming is it can only handle client jobs of MapReduce type. Okay, so it can only handle jobs which would fit into this architecture of having a mapper and a reducer running. But let's say in the market we might have various different kind of architecture, and I could have a client who wants to run a job different from this architecture of mapper and reducer. So that cannot be handled by this Hadoop version 1, by this architecture of job tracker and task tracker. Okay. So to counter these shortcomings, they thought of something called as a yarn, or a yet another resource negotiator. Now from the name you can understand we are basically targeting this number 2 shortcoming. By the name you can understand that. Okay, yet another resource negotiator. Earlier, every negotiation in terms of each job, what are the resources they require, it was all handled by this job tracker. But somehow with Yarn, we are trying to distribute this responsibility to some other task, which we will talk about very soon. It's actually called an ApplicationMaster. Okay, so this, when we could handle this possibility, right, we were also able to handle the number 3. So it allowed us not only to manage resources independently, but also it allowed us to handle different kind of jobs which are different from the MapReduce architecture also. And to handle this single master or single point of failure thing, we actually included the high availability, right, that we talked about in HDFS also. So when we discussed about the secondary name node and everything, right, so that was basically HDFS 1, which was introduced in Hadoop version 1, wherein we have a single name node which acted as a master, and a secondary name node which was not acting as a master, but it only was keeping a track of the metadata. That was all in Hadoop version 1. So in Hadoop version 2, they first introduced the highly available environments, wherein we had a name node active and standby. And following the same approach, they included in Yarn, the master would be now, one of them will act as an active, while the other will act as a standby. Okay, so this was handled by introducing the concept of high availability in Hadoop version. So on that note, let's quickly discuss what is the architecture of this Yarn and how does it counters the shortcomings of the Hadoop version 1 or the job tracker and task tracker architecture. Any doubts so far? So far we have already discussed about what we are targeting, what we had. So we are targeting a distributed computational environment. What we had was RDBMS, but that was transmitting large data over the network. It was clogging the network. So we come up with this Hadoop version 1, which was able to at least handle these shortcomings, but it introduced few more shortcomings, that needed evolution, and it was evolved into Yarn, which we currently use in most of the environments that you see, or in any Hadoop environment or distributed environment which is running computational. It's basically using this version 2 because of the liberties that comes with it. Okay, so the Yarn architecture. Okay, so the job tracker in Yarn, which was in Hadoop 1, so the job tracker is replaced by a task by resource manager. Okay, the task tracker is replaced by a node manager. Okay, this is my master layer. Now, resource manager can be in active standby or highly available. This was not highly available, while somehow the task tracker are quite similar to node manager, but the only case is task tracker was only useful when it was to run a mapper or reducer task, but node manager now it can run different kind of architectural tasks as well, not just the mapper and reducer task. Okay, and there was a new temporary master which was introduced in Hadoop 2 or Yarn, which was called the ApplicationMaster. This was a temporary master associated with each job that ran on the cluster. Okay, so for each job that ran on the cluster, this temporary application master will be launched, which will take care of that particular job. So now you can see this job was actually also being done, was also handled by the job tracker in Hadoop 1. But now we have, so the job tracker was not only handling for each application, but it was also handling all the applications. So now we have distributed that responsibility into two. One is resource manager, which is only responsible for the multiple jobs and their resources needs, while the application master will now be responsible for its respective job. So we have distributed these responsibilities among two separate processes in Hadoop version 2, and that's how we handled this shortcoming of overburden master. Okay, we have handled this shortcoming of single point of failure. Sorry, this shortcoming of single point of failure by having an active and a standby resource manager or master player. Okay, so let me just draw its architecture diagram. So we have an active resource manager. We also have a standby resource manager. Again, Zookeeper is taking care of which one is active, which one is standby. Zookeeper, whenever it comes to handling the active and the standby states, it's actually the responsibility of Zookeeper. And then you have various node managers. Okay. Mostly you will see the node managers are running on the same host where you have data nodes because of the concepts of data locality. Okay. Now client will talk to the resource manager. Client will talk to the resource manager. It will distribute that job among the node managers, and each node manager is running either a container container or containers, I would say, and it may also be running an application master. So application master will also run on the node manager. So for each job, let's say this client one has run a code logic.py. So each job will run many containers over different node managers, and all these containers will be managed by the temporary master associated with that job, and that will be called as a application master. Okay, so you can have multiple jobs, multiple client running their jobs over the resource manager, and the application master will be responsible for each job and its resources, while resource manager will only be responsible for the application masters associated with each job and what are the resource requirement for each of the application master and its associated containers. Okay, and this also introduced the liberty to run any kind of job. We can run not just MapReduce, we can run MapReduce kind of job, we can run Spark architecture, we can machine learning, artificial intelligence, all these fancy words that you have heard of. This Hadoop version 2 gives you the liberty to run any of such different architecture, which can be different from the MapReduce architecture also. So it depends you. If you want to run any of these, you have the liberty to run it over the Hadoop version 2. So I think that's all in terms of the theoretical stuff that I would want you to understand. And in the next class, we will take it from here and discuss more about the practical stuff, how our job runs, where can you see your application master, and what are the responsibilities when it comes to the Hadoop administrator when it comes to managing all this. Okay. But for now, just try to understand this architecture and let's relate this to what we see on our Cloudera manager. Okay, so this is my yarn page. Let's go to the instances. So right now you can see a node manager, you can see a resource manager active because we didn't change anything here. So we at the time when we installed, we only had one node. So only this 176 was there. So the node manager was also installed on it, and the resource manager was also installed. You also see one more thing called a job history server. This is just keeping a track of the various job history, uh, the various jobs actually that ran on the system on the cluster. So let's include that also here. So all the historical jobs which are running within the cluster, which ran within the cluster, the job history will take care of its keeping a track of it. Now, for having such an architecture where we have a standby resource manager and two more node managers, I will add few more roles over here. Add roles. I want to add another resource manager. Let's add it on this node. And I also want to add two more node managers. Okay, so now we have three node managers. One is active. When I start this, it will come up as a standby. So let me just restart what all is required. Okay, so in the next class, I'll show you the UI, how from the UI you can handle, you can manage these resources. Most part of a Hadoop admin, is to deal with. So you can have issues with these jobs. Some people, some client will come to you and say, I'm not able to run a job, or my job is failing. So what is the approach in such a scenario? How do you tackle such a situation? That's what we have to understand. But yes, we must know this architecture, because only when we know this and how it actually interacts within it, then we can quickly go to the issue and try to and solve it easily. So in the coming week, I want everyone to read more about yarn, make yourself comfortable with yarn, have three nodes, try to explore more about it. So when I say explore, how do you explore it? So everything is available in this Cloudera manager. You can go to the config section, you can go to the stat section, or you can come to the server. So play around with it, play it your way, come up with something new also. If you come up, if something new that you can observe about yarn, that would also be good. But yes, for the general case, just at least be comfortable with the architecture, how everything is running. Try to read the logs, and it will make you more comfortable with this. Okay, so now you can see we have 2 node managers, 3 node managers, and 1 standby and 1 active resource manager. I think this 2 has some issues. We might solve it in the next class and make it running also. Okay, so that's all for today. Any questions, any doubts? Let me share this to the group.
Sahil, this is Tasnim.
Yes, Tasmin.
Also, on the resource manager schedule, so does it like restart like any failed task?
Which task?
Like any failed task, the scheduler, does it restart automatically?
Yes. Let's say this client ran a job and the application master was running on this node. Okay. And somehow I lost this node. So what will this resource manager do? It will relaunch this application master on some other node manager. Similarly, since the application master is responsibility is to manage the containers within it, so if any container somehow it fails, application master will relaunch that container either on the same node or on some other node. So any intermittent container failure or application master failure will be handled by resource manager and application master, and those will be relaunched.
Okay, thank you. I do have some other questions, but you said like you will talk about the practical stuff about next class, then I'll ask on that class. I had some
That's fine.
questions.
If you still have questions, you just put it on the group.
All right.
Okay.
I just have some 3 or 4 questions, like how to kill job using yarn, like running jobs on the log.
I will show you all those stuff. So for killing job, you have this command yarn. I think application -kill, then the application ID. To check logs, you have command yarn logs application. I will go more deep into such things in the next class. I will show you. I will launch an application. I'll show you how you kill it, how you check the logs. So don't worry about it. Okay. All those practical stuff we will discuss in depth in the next class.
All right, sure. Thank you.
Okay. Any other questions, guys? Okay. If you don't have any other questions, I think we are done for today. Any doubt? Just if you have, you can anytime put on the group and do study about yarn. Don't lag around. I think it's this time that you are into, it won't come back again. So put all your efforts. That's all what I can say. And I'm there to help you out, and I'm also there to learn from you. Okay, so we've come up with something new also within Hadoop that you could explore and I didn't. So okay, on that note, thank you for joining. Good night.
Thank you. Thank you.
Thank you, Sahil.
Thank you.